Alright. Well, I wonder if anyone else is gonna show up. How many people are watching this right now? There we go. That's what I want. Stream key that I'm using. Not the one I want to do. Oh, okay. That's working. Cool. Alright. I think I finally sorted everything out. Okay. Cool. Alright. I think I finally sorted everything out. Okay. Let's see. So I opted to, I'm just gonna go solve some of these problems. Let's start with this. Cool. Alright. I think I finally sorted everything out. Alright. Ooh, wow. Okay, huge. Alright, so I think I'm just gonna go over some of these equilibrium problems. Okay. So I opted no particular order solve some of these problems. Let's start with I guess this. I'll just pick one that looks interesting. Cool. Right. So I think these were kind of the ones that might have given you guys a lot of issues. I don't know, it seemed like they'd give you guys a lot of issues, so I'm just gonna pick one. Let's start with let's start with, I guess, 50 looks good. So let me just cut this out. I'm gonna have to cut some more out later. Okay, that out. Alright, so now while you guys are watching this, if you have any questions, feel free to type them into the chat so I can get to them. Otherwise, I'm just going to solve these as I would, and I'll talk my way through it. And hopefully you guys can follow along, okay? Again, if you have any questions while I'm doing this, feel free to ask. Okay. So this question asks us, or tells us, at a certain temperature the KEQ is equal to 4 for this particular reaction. Predict the direction in which the equilibrium will shift, if any, when the following systems are introduced into a 5-liter bulb. So this is basically 3 different calculations. You're kind of doing the same calculation 3 different times. And this is asking us which way the equilibrium will shift. So we have to define Q, which was our, what do they call it, reaction quotient. I think they call it the reaction quotient. Okay, so what we can do then is we say, okay, my reaction quotient is going to be concentration of products over concentration of reactants. Okay, so we'll have to calculate the concentration of the products. In this case, the concentration of H2, which is 2 moles. I should say this is for A. 2 moles over 5 liters. So this will give me concentration of 0.4 molar. Then we'll take the concentration of fluorine, which is 4 moles over the same container, 5 liters. Should be 0.8 molar. And then finally the concentration of the reactants, which is HF, and this is 3 moles over 5 liters. So this is 0.6 molar. Alright, so now we calculate Q. Q will then be concentration of H2 times concentration of F2 all over concentration of HF squared. Products over reactants. So calculating this out, this will be 0.4 for the H2, 0.8 for the F2, and then we get 0.6 squared for the HF. Okay, so then calculating Q, let's see, let me pull out my calculator here. Calculating Q will get me, so we got 0.4 times 0.8 divided by 0.6 squared. So this gets me a Q value of 0.8 repeating, so we'll go 0.89. Alright, then we compare this to K, and K is equal to 4. So Q is much, or it's not much less, it's just less than K. So with Q less than K, this means that this reaction will proceed forward. So reaction moves forward. Reaction moves forward. Because the reaction has not reached equilibrium yet, it wants to get the ratio of products and reactants to this number. So this reaction will proceed forward until the ratio of products, so let's highlight that in a different color, the ratio of products to reactants in this equation is equal to this number here. Yeah, it's much less, so it's going to move forward. Alright, B is kind of the same thing, we just change the concentrations of HF, H2, and F2, but you would basically the same calculation and you would check. How does Q compare to K? And then the conditions were, if you remember from our notes the other day, the conditions were if Q were less than K, reaction moves forward, which is what the case we got here. Okay. If Q is greater than K, then reaction goes backwards. Reaction moves reverse. And if by some miracle K is equal, or Q is equal to K, then reaction is already in equilibrium. Reaction in equilibrium. Alright, so the reaction actually won't do anything. Alright, so that's question 50. So that's an example of, I think this is like the 4th example we did in the last couple of days, but there you go. No ice table necessary for this. It's just a straight application of, well, not really a straight application because we had to calculate Q, which was something different than KEQ, but same idea applies. All right, let's pick another one. So that was 50. Let's see. Let's grab, oops, totally not mean to do that. Let's grab another one. Oh wait, same. There we go. All right, scale this up. Let's do, let's see, whoops. 51 asks certain temperature KEQ is equal to the following. Predict the direction in which the equilibrium will shift, if any, when the following systems are introduced in a 200-liter bulb. Same, that question 51 is the same as question 50. 52. KEQ is equal to 5, certain temperature. That reaction. Okay, here's one where, let's do this one. Alright, let's do this one. So this one will require the use of an ice table. So let me write out the reaction. 2SO2 plus O2 going to 2SO3. Okay. Let's get my ice table all set up nicely. As follows. There we go. All right. ICE. There we go. Okay. Just a minute. Gotta check on something. Okay, good. All right. So here, this question, so at equilibrium, we contain 0.3 moles of O2. So I'll put 0.3 moles. Divide this by volume. This was a mistake I made several times. Maybe not several times, but definitely one glaring mistake I made. So make sure you guys divide. Because remember, the ice tables can work in either moles or concentration. It's probably easier to work with it in concentrations. Okay, so this means then that, let's see, 0.3 divided by 2, so I should have been able to do that, 0.15 molar. Okay, they say a certain amount of SO3 was placed in a 2-liter vessel, so we'll call this X, and we'll assume we don't have any of these because we're not told about it. Okay. The only way that this reaction can go is backwards then, so the change would have to be, this would have to get used up. We'll call that 2y though because of this. This will have to increase by some amount, and this will increase by some amount. Okay, now from this data, let's see, is that all I need? Yeah, from this data we can calculate what the change in y is, because we know that y has to be this, because that's the only way that we can get this 0.15 is if by increasing the amount of O2. If we started out with no O2 and we end up with 0.15 molar, the change in y must be 0.15 molar. So this means then that if y is 0.15 molar, then 2y will be 0.30 molar, or 0.3, depending on how many significant figures you want to keep. Okay, and then over here, this will then be x minus 0.3 molar as follows. Okay, so now we've got all the equilibrium concentrations. We can then set up our KEQ equation. So KEQ equals concentration of products, which is SO3, concentration of SO3 squared, because we have 2 of them, divided by concentration of SO, and I think we have 2 of those. Oh, yep, it's SO2, sorry, squared, and then concentration of O2. And then when we fill in the values with our equilibrium amounts, we get SO3 is x minus 0.3 squared. SO2 happens to be 0.3 squared, and O2 happens to be 0.15. And I think KQ was given to us as 4, I believe. No, 5, given to us as 5. Alright, so there's 5. Okay, so doing some algebra, we now get the following. So I'm going to multiply the 0.3 squared by the 0.15, and this will all be equal to x minus 0.3, and this will be all squared. Okay, I can square root everything like that, so I can get rid of this, and then I can add the 0.3 to this side, so I can get x by itself. Alright, and then we throw that all into our calculator, and that'll give me what x is equal to. Alright, let's see what we get. So we're going to take I should throw this into scientific mode. Okay, so we are going to take the square root of 5 times 0.3 squared times 0.15, and we're going to add to that amount 0.3. Alright, so here we get x is equal to 0.5598, so I'll just go 560. That'll be in molarity. Alright, now going back up here, now we know what x is. Is that what we're looking for? Oh, yeah, there we go. So we know x is then, this is the initial starting amount. So initial amount of, or sorry, not initial amount, initial concentration. Initial concentration of SO3. Now, is that what the question was asking us? The question was asking us, oh yeah, just concentration, okay. That's not so bad. That's a little easy to work with. Initial concentration of SO3. Alright, there we go. Alright, let's go find another one to do. If I paste image again, let's see what other one. Okay, so that was 52. Let's see, 53 asks us at equilibrium in a certain vessel, what is the equilibrium concentration of Cl2? Do I want to do that one? What's the next one? That one seems too trivial. 125. Well, let's see. We have moles of HI, moles of H2, moles of I2 are thrown into a vessel. Will the reaction proceed to the reactant side or product side? As because 54 is basically the same as question 50 from earlier. Yes. 55. Reaction mixture at equilibrium, CO plus H2O going to CO2 plus H2 contains 1 mole of, okay, 1 mole is added to the system. Calculate the concentration of CO, which will exist when that's a good one. I like this question. Let's do 55. Okay, so this is one where you have 2 equilibriums. This is a double equilibrium kind of question. All right. Okay. So, because we have an equilibrium amount, because it's here at equilibrium, we have this. Okay, and then then we add this much, and we look for a new equilibrium. So we can use at first equilibrium. We can calculate K as concentration of product, so CO2 H2 over reactants, CO over H2O. Okay, they're all gases, right? Yes. Sometimes a question like this might throw something that's not a gas at you, and it might, and then you don't have to worry about it. So if there's a solid, you can just ignore it. Or if there's a liquid, you can just ignore it. But thankfully all of these are all gases, so everything has to be taken into account. Anyways, on to calculate the equilibrium concentration. So CO2 will be 2 moles in a 2-liter bulb, so that's 1 molar. They all have 3 significant figures. Concentration of H2 is 1 mole over 2 liters, so that'll be 0.500 molar. Concentration of CO, 2 moles over 2 liters, so that'll be 1.00 again. And concentration of H2O is also 2 moles, so this will also be 1.00 molar. This makes my KUQ calculation surprisingly easy because CO2 will be 1, H2 will be 0.5, 0, 0. CO will be 1.00 and H2O will also be 1.00. All right, this just ends up being 0.5. Okay, so there you go. So now we got KEQ at the first equilibrium. Okay, so at second equilibrium, this will require the use of an ice table. Okay, so at second equilibrium, how much are we adding again? I should make note of that. We're adding 1 mole of H2. Okay, so at second equilibrium, okay, at second equilibrium, we will end up getting, yeah, we need an ice table, so should go make sure now. So CO plus H2O going to CO2 plus O2. So CO plus H2O going to CO2 and H2. Okay, and I think it's balanced already, thankfully. Okay, so no need to worry about that. Set up our ice table. Follows. Alright. ICE. Okay. Right, and then we add 1 mole of H2, so that'll change my H2 concentration to be surprisingly 1 molar. Okay, all right, so everything then ends up with a concentration of 1 molar. Okay. Now, if you don't quite understand how H2 becomes 1 molar, we'll go back to here, and the new concentration, since we're adding 1 mole. So here it is, adding 1 mole. So then the new concentration of H2 will be 2.00 moles over 2.00 liters for 1.00 molar. All right, this is surprisingly easy now. Why? Well, this is how the reaction will proceed. We've added more of this. So this reaction has to proceed backwards. So this will be minus X, this will be minus X. This will be plus X, and this will be plus X. Okay, so then this will be 1.00 plus, keep forgetting proper significant figures. 1.00 plus X, 1.00 minus X, and this will be 1.00 minus X. Okay. And then now we have our equilibrium concentrations. We also know what our KEQ is from the first equilibrium, so we can set up the next equilibrium expression. So we got KEQ equals concentration of products 1.00 minus X over concentration of reactants. Okay, and we know what the KEQ value is. It's 0.5. 0.5, there we go. Looks like I messed something up. Seems too easy. Products, reactants. Nope, everything looks good. Okay. Then we'll do the following. We get 0.5 equals 1.00 minus X squared over top of 1.00 plus X squared. I have squares on the top and the bottom. It's probably easiest to just square root everything, so I can get rid of that. And then we get square root of 0.5 times 1 plus X equals 1.00 minus X. We end up getting the following. This becomes root 0.5 plus root 0.5x equals 1.00 minus X. This then ends up becoming, I'll bring this X over to this side, and I'll bring this to the other side, so we get root 0.5x plus X equals 1.00 minus root 0.5. Okay. Ugh, so close, not quite. I can factor an X out of here, so this becomes square root of 0.5 plus X. And then this becomes 1.00 minus 0.5. Oops, that's not a plus x, that should be a plus 1. Oh, let's shrink that a bit. There we go. Wait, no, that one's right, it's this one that's wrong. Alright, so this is 0.5 and this should be a plus 1. Okay. And then we get the following. X is then going to be 1.00 minus square root of 0.5 all over top of square root 0.5 plus 1. Okay, and then let's carry out that calculation. So carrying out that calculation, we get the following. Let's see, 1 minus square root 0.5 divided by square root of 0.5 plus 1. Oops. Properly in my calculator. So I got an answer of x equals 0.1716. So that's the change. Alright, looking back at my ice table, looks like it'll work out okay. So all the concentrations are 1 plus or 1 minus. Oops, 1 plus or 1 minus that. So we're interested in the equilibrium concentration of CO. So CO is 1 plus. Oops, CO is 1 plus that, as can be seen here. So let's do that. So concentration of CO will be 1 plus x. So this is 1.00 plus 0.1716. So the concentration of CO will be 1.17 molar. There you go. There, that was fun. A little long and tedious, but it looks like the algebra worked out quite nicely. Alright, okay, let's pick something from a different set. That was from 50 to 55. Let's grab one from here. Alright, these ones are much more interesting, these ones. So that's 55. Alright, what's 56 say? 56 states the following. Student obtained the following data at 25 degrees Celsius while studying equilibrium. Oh, hello. All right, hey, you got someone watching. Cool. Okay. Where was I? Yeah, 56. 55 was interesting. 56. Student obtained following data 25 degrees Celsius while studying the equilibrium. Calculate the moles of Ti plus present in the second data set. That one? I don't think it does anything like that. Let's work through it. All right. All right. I oddly enough think 56 is very similar to 55. It's just worded slightly differently. We have enough information at first equilibrium. It looks like we have two equilibriums to work with. So at first equilibrium, we can calculate KEQ. Oh yeah, this actually works out just fine. Haha. We can calculate KEQ as, yeah, products over reactants. But this one's trying to be a little sneaky because one of the products is a solid, and at the same time one of the reactants is also a solid, so we don't actually need to worry about those. So the only thing we need to worry about is the cadmium 2 plus concentration and the titanium? I can't tell. It's either titanium or thallium. If it's thallium, this is gonna really mess things up a little. Well, maybe not. It might not mess anything up because it doesn't look like we actually need the molar mass. We'll say titanium. Anyways, because of the solid nature of the this reactant and this product, we don't actually need them in my equation, so I can just use this. Why did they not give us nice numbers for this? Whatever. Okay, concentration of cadmium 2 plus. At least the first one's a 1 liter container, so that's easy. 0.414 moles divided by 1.00 liters. Easy enough calculation. And then repeat for the concentration of the titanium. I'm just gonna pretend it's titanium. Sometimes I can't tell whether it's an I or an L. So this becomes 316. Okay. And then we can throw that into my KEQ calculation. So 0.414 over 0.339. Altogether we get something I cannot do mentally. So here we go. 0.414 divided by 0.339. I get a KEQ of 1.22. Alright, so there's the first equilibrium KEQ. Okay. Now, I think the problem says, okay, so they increase the volume to 5 liters and they record what happens. So let's figure out new equilibrium. Do I even need an ice table for this? I don't know how much is being added, but I do know that I do have my volume. I do have this, so at the very least I can do the following at second equilibrium. At second equilibrium I can calculate the concentration of cadmium 2 plus. That is 0.339, so 0.339 divided by 1.0, no, not 1.00, but we changed the volume. The volume changed. The volume changes to 5. Alright, so now the concentration of cadmium changes, so 0.339 divided by 5. So now the concentration is 0.0678 molar. Okay, so there we go. Can I do anything with that? Well, I think I can, because I know that my KEQ is constant and I'm not changing the temperature because the question explicitly tells me that I'm operating at 25 degrees Celsius. So if KEQ remains constant, then I can write the following. I can say this: KEQ equals concentration of cadmium 2 plus over titanium plus. Did I miss anything? Oh, I did miss something. That should be a titanium squared. I have to go change some things now. Alright, so this is actually not correct. I forgot to square the titanium concentration. Let's highlight that in a slightly different color so you guys can see my mistake. There we go. Okay, let's recalculate KEQ. I knew something was fishy. 414 divided by 0.339 squared. Sure, right, I don't trust it to do it that way. 0.339. There we go. Okay, so KEQ is actually 3.602. I'll keep an extra significant figure just in case. All right. Okay. Does that change what I do in the next step? Surprisingly, no, it does not change what I do in the next step, but I should put a square here. Did I write that in my original KEQ? I did too. I did write it down. I just missed it. Whatever. Alright, now that I've got the correct KEQ, I can then do the following. 3.602. And this will allow me to calculate for... Ooh, I can calculate for this. Okay. So to calculate for the concentration of the titanium plus... I can say the following. This is going to be concentration of cadmium 2 plus divided by 3.602. And I know the concentration of cadmium 2 plus because I have enough information to calculate it. So let's do it. Oh yeah, and then to get rid of this square, I can square root that. So concentration of titanium is going to be the square root of 0.0678 divided by 3.602 equals, let's see, square root of 0.0678 divided by 3.602 is 0.137 molar. Right. Oh yeah, Connor, did you let anyone else know I was doing this? Or did you keep that to yourself? Alright, we're not quite done yet though. Because the question was asking me to calculate the moles of Ti plus. So I have the concentration. So remembering concentration is moles per liter, I have a 5-liter container, so I can say moles of Ti plus is going to be 0.137 molar times 5 liters. So that will be 0.686 moles, I think. There we go. There we go. Okay. Alright. That works out quite nicely. That was fun. Kind of a little bit different than the previous ones. This one didn't actually require us to use an ice table because we didn't actually have any information about what was added or what was taken away. We were just given volumes and we had to work with it. But we had enough information to solve it in the end. Still recognizing this was a first equilibrium and a second equilibrium style problem. Alright, okay, let's look for another problem to work on. Alright, so that was 56. 57. Excuse me. 5 moles, oh sorry, 0.5 moles of NaCl. Put into a flask. Allowed to come to equilibrium. Moles of Cl2 found. What is KEQ? That one seems simple. Do that one. What's 58? 58 gives us KEQ in a reaction. That's another. How many moles of H2S were originally in the flask? I think I did one already like that. The only thing to watch out for in this one is that they give you moles and not molarity, and they ask you for moles after. That's kind of the only thing you have to ask. But it's similar to one of the ones we answered earlier. 59. Reaction mixture at equilibrium. It contains moles of stuff. How many moles of CO2 would have to be removed from the system in order to... Ooh, this is a good one. Let's do this one. I like this. Whoops. I like this one. So this was this one. Ooh. All right, I like this one. This one's good. Okay, so at a reaction mixture as follows. We have a bunch of stuff at equilibrium. So at equilibrium, so first, geez, can't spell today. First equilibrium. So at first equilibrium, we contain. Let's see. Good. Oh, cool. There are more people. Cool. Well, that's okay. So at first equilibrium, we can calculate the following. We can calculate KEQ as concentration of CO over concentration of H2O. Again, products over reactants. All right. Again, if you guys are watching and you have any questions, or if there's a specific question you guys want me to answer, let me know and I can do that one next. At this point, I'm just picking ones that I think are interesting. All right, so we can do this at first equilibrium. Let's calculate the CO. Actually, the CO2 is listed first, so we'll do that. 4.00 moles over 5 liters. So this is going to be 0.8 molar. Next one is concentration of concentration of H2, 1.5 moles over 5 liters. So this will be 0.3 molar. Concentration of CO equals 3 moles over 5 liters, so that's 0.6 molar, and then concentration of H2O is 2.5 over 5, so that'll be half a mole, or half a molar. Alright, throwing this all into here, nothing, no squares necessary, so that's good. CO, so 0.6, H2O is 0.5, CO2 is 0.8, and H2 is 0.6. There we go. Can I do that one? Wait, nope, I messed up. That should be H2, which is 0.5. This is supposed to be H2O, which is... Oh wait, that one is right. What am I doing? This is supposed to be 0.3 because that's concentration of H2. 0.3. Okay. And calculate all this out, and we get... What do we get? 0.6 times 0.5 divided by 0.8 and 0.3. KQ is 1.25. Okay. Right. Just a moment. Oh, cool. Okay. All right. Okay. Oops. Cool. All right. Connor asks, would the addition of a solid liquid reactant or product affect the equilibrium constant? No, it would not. The solids and liquids, because of their constant density, have constant concentration, so it's already taken into account with the equilibrium constant. It makes dealing, if you have any solid or liquid reactants or products, it makes the math a little easier because you can be happy knowing that the constant nature of the solid and liquid are already taken into account in the KEQ number. Okay. Where was I? Oh, right, okay. So we've got first equilibrium constant, and now it asks us how many moles of CO2 have to be removed from the system in order to reduce the amount of CO to 2.5 moles. All right, so our target concentration at second equilibrium. So at second equilibrium, we want to get the CO to be at 2.50 moles, and so at the concentration, we want to reduce the concentration of CO to this 0.5 molar. Okay, this is good because now we know what the equilibrium concentration needs to be. So when we set up our ice table, we'll have the following. Shoot. What was the reaction again? CO2 plus H2. Okay, so we'll get the following. So we got CO2 plus H2 going to CO plus H2O. I keep feeling I messed up again. No. Okay, I'm good. I am good. Okay. So hopefully that answers your question, Connor. I wonder who else is watching. I'm always curious. ICE. Alright, so we have our target CO concentration. This wants to be 0.5 molar. The initial amount of CO would then be 0.6 molar. So this is 0.6 molar. Then the other values, H2O was 0.5. Okay. H2 was 0.3, and CO2 was 0.8. Okay, and the question wanted us to how much CO2 needed to be removed from the system in order to reduce the amount. Okay, so if in order to reduce, I have to figure out this needs to change. So I'll highlight this. So this needs to change. This needs to be reduced. Okay, so I probably shouldn't actually leave it as 0.8 molar. What I should actually do, write it like this. So not as 0.8 molar. I should write this as X. So we want to reduce it to some number X. Okay. All right. Now, what this means then is if I want to remove some of this. I don't know how much, so I'll leave that as X. But I do know that at the end I want my CO concentration to go down, so I can put down a minus Y here, because that's what I want to do. I want to force this to get smaller. So that's my change. So that's fine. Now I can put the following. This is going to change by Y. If this side is getting reduced, this side needs to increase, and this needs to increase. Okay. Now again, you're going to run into a situation where you have two variables. You have an X and a Y, but because of this column, so this column here, we can actually calculate what that Y change is going to be. In this case, the Y change is going to be 0.1 molar. So if Y is 0.1, this will then become 0.4 molar. This will become 0.4 molar. This actually sets us up amazingly well. So this is great. And this will be X plus 0.1 molar. Why is it going to set us up really well? Well, you guys can where's my K? KEQ is 1.25. Okay, KEQ is 1.25. So we can say the following: KEQ equals 1.25 equals concentration of CO, concentration of H2O over top of concentration of CO2 and concentration of H2. Now, when I put in the numbers, I should really do this proper. When I put in the numbers, my concentration of CO is 0.5, my concentration of H2 is 0.4, concentration of CO2 is X plus 0.1, and concentration of H2 0.4. Looks like OHs. I should really make that more clear. 0.4. Do the same thing over here. Alright, so like I said, the math is surprisingly easy because these drop out. Okay, and then we get the following. We get, after I move those two due to algebra, x plus 0.1 equals 0.5 divided by 1.25. Move that over, so we get x equals 0.5 over 1.25 minus 0.1. So x is going to equal, let's pull out my calculator. Yeah, this feels like this is something I should be able to do without a calculator, but can't. So x is 0.3 molar. Alright, we're not done though, because this is this is not what the question was asking. We're almost there though. The question was asking how many moles of CO2 I need to remove. So now I know what the concentration is. Okay, I know the concentration of CO2 that I want. The concentration of CO2 that I want is 0.3 molar. And the volume of the container is 5 liters. So I can at least calculate how many moles of CO2 I have. So moles of CO2 will be 0.3 molar times the 5 liter container. So that'll be what, 1.5 moles? Okay, so that's how many moles of CO2 are present if I want this, if I want to force the condition that it asks me to. And I started off with 4 moles of CO2 up here. So if I want to go down to 1.5 moles of CO2, I have to remove. So therefore remove 2.5 moles of CO2. There we go. There. That was fun. I like that question. Really like that question. Okay, for those of you guys watching, that's probably gonna mean I might throw that onto your test tomorrow. Wonder if that gives you guys an unfair advantage. Well, if you did let the class know, then everybody knew that this was gonna happen. So I guess it's not really that unfair. Anyways, let's see. So that was question 59, was it? Yes, that was question 59. What's question 60? Let's look at question 60. Question 60 asks us, let's see, some reaction occurs at a certain temperature. We have moles of H2 and I2 permitted to react, then goes to equilibrium. What will be, okay, we did that example in class, so I think I can skip that one. Let's go look at the other questions. Well, I shouldn't say we did that exact example. We did a very, very similar example in class, so shouldn't be too bad. Should be easy to do. Alright, 61. Alright, equilibrium constant for this reaction is as follows. NH3 was added to the container so that there are 2.5 moles of N2 at equilibrium. How many moles of NH3 did we start with? We did that already in class. 62. Equilibrium constant. Oh shoot, lost my place. Equilibrium constant, 0.15 moles of N2O and 0.25 moles of H2O were put in a bulb, allowed to come to equilibrium. What concentration of N2O2 was present at equilibrium? This sounds very similar to something we did already in class, so I'll skip that one. 63. Reaction at equilibrium. We have mole amounts of everything. Add some stuff to it. New equilibrium. 63 is actually easier than 59. Okay, but we did an example like that in class, so I'll skip that one. 64. Reaction mixture 2NO contains moles of stuff. How many moles of O2 had to be added to the mixture to increase the number of moles of NO2 to 1.28 when equilibrium was established? So 64 is actually very similar to 59. It's just rather than removing the number of moles, we're adding the number of moles. So I think the change will have to just be slightly different. Let me set that up for you. I'm not going to solve it, but I can at least set up the equation for you. So the second equilibrium ice table would look like this. 2NO plus... Oh, hey, there's squares in this one. To do this. No, the squares will just basically just make the algebra look scary. But ultimately the algebra is not really that scary, it's just long, not difficult, long. As long as you don't mess up any of your steps in the algebra, you should be fine. But let me set up the ice table as to how this should look. I won't solve it though, because like I said, it's very similar to 59. So you set up this way. We don't know what this is. The moles of NO2, we want this to get to 1.28 moles, but work with this in concentrations. So there we go. The amount of NO2 initially would be 1.2 moles over 2.00 liters. That'll give you some concentration. Okay, so this will give you some concentration. Since we're increasing the concentration, this will be plus y, but since we have this 2 there, it'll be plus 2y. This will be minus y. This will be minus 2y. Yeah. There we go. So this is how you would set up the ice table. So this ends up being x minus y. The NO, this would be 0.240 over 2 liters equals some amount. So it'd be whatever this amount is minus 2y. There you go. So that's how you would set up the ice table for 64 and then solve it that way. Just be mindful of the algebra in this question, because you've got this will be squared, this will be squared, so it might be more quadratic in nature than the one we did in 59. Alright, 65. Reaction mixture as follows, found to contain some, is that ICL? Yeah, it must be ICL. Moles. How many moles of ICL would have to be removed in order to reduce the concentration? So 65 is pretty much the same as 59. Alright, that leaves us with this last one, the nasty one. This one might actually take a little bit of effort because I don't think I've actually solved this one before. I feel bad for saying that, but that's okay. We can work through it. Okay. So it tells us that there were some CH4 and H2S in a 1 liter bulb. At equilibrium, we have the following. And we want to know what is the concentration of CS2. Okay. We have a lot of unknowns to work with. So this is going to be lots of fun. This is going to be a fun problem. Very, very fun problem. If you can consider this fun. Anyways, okay, so let's set up my equilibrium ice table as follows. So we have CH4 plus 2 H2S going to CS2 plus 4 H2. think part of the reason that they mention this is nasty is probably because you're going to end up having to take a fourth root of something. I mean, it's not the end of the world with graphing programs. If you have graphing programs, solving the KEQ equations is relatively easy because once you get the equilibrium expression, you can just throw it into Desmos or GeoGebra and solve it that way. Okay. Anyways, we don't know what this is, so we'll call this X. We'll call this Y. Okay. As you can see, it's already going to start looking really, really crazy because we've already identified two variables. We assume we have none of that. Okay, otherwise it makes the problem ridiculously difficult. Okay, this is gonna change by some amount. We'll call that Z. Call that this will be 2Z. So this will be plus Z and this will be 4Z, like that. Okay, and then this ends up being 4Z, right? And this ends up being Z. This, oh, we actually know what this is because it tells us at equilibrium we have 3 moles of H2S. So this is great because then I can just do the following. So this might actually alleviate some of the issue. Oh, and look, we have a 1 liter container. So this is actually even better because then I don't have to worry about concentration math. I can just write moles. So 0.3 molar. And this will be 0.1 molar. Okay. We should be able to figure out what Z is. Hopefully. That's what we want to try and figure out, is we need to figure out what Z is before we can actually proceed with this. Like, or do we need to? No, we don't actually need to because we already know what our equilibrium concentrations are. So this information here is actually semi-pointless because we have our equilibrium concentrations. Okay, so let's throw that in, and we have our KEQ here, so that's good. So we can write the following. Okay. It's somewhat counterintuitive because I guess for this particular question, a lot of people might not understand that they can assign variables to everything that is unknown. It's something that's not really talked about in a lot of math classes, is that if you don't know something, just give it a variable. And honestly, even when I was teaching math, I don't think I ever mentioned that to my students. So it's not really your fault that if this assigning random variables is new. Anyways, going on. So this will be Z. Okay. Wait, what am I doing? Product over reactants, right? Product over reactants. That's what I'm doing. All right, sorry. But let me rewrite this so it's explicit what I'm doing. All right, so CS2, H2, but then that's 4. H2 to the 4. Reactants, so CH4, and then this will be H2S squared. Okay, explicitly I'm calculating KEQ. Let's throw down some numbers, or I guess in our case variables. CS2 is Z, H2 is 4Z to the 4th, CH4 is 0.1, and H2S is 0.3 squared. Oh, this actually isn't so bad. I don't know why they said it was nasty. I thought it was going to be some crazy binomial 4th root or something like that. But this is actually not so bad. It's actually not so bad. Alright, so let's clean things up a little bit. 4 to the power of 4 is, I think, 256. I want to say it's 256. Let me just check to make sure. 4 times 4 times 4 times 4. Yep, 256. So 4 to the 4 is 256. This ends up becoming Z to the 5th. On the bottom, we get 0.1 times 0.3 squared. So this is 0.009. Okay. And then some more algebra later. 009 equals 256 z to the 5th. Divide by 256, divide by 256. That drops out, so z to the 5th is equal to divided by 256. This is not a very nice number. 0.003515. Let's go to 116. Yes, that's what they'll round to. There you go. Okay. And then yeah, it's not so bad. I don't know why they call this nasty. Unless I missed something. Which is quite possible. I don't actually have the textbook, so I don't actually have the answer key on hand. So it is quite possible I missed something. Anyways, 5th root of this, and that'll be equal to z. 5th root. So the 5th root of this number, 0.003516, taking the 5th root, I get an answer of 0.323. And oh, that'll be in moles. It's a 1 liter container, so it doesn't matter. Molar. Alright, now what was the question asking us again? The question was asking us what concentration of CS2 at equilibrium. CS2 is Z, so there we go. There's our answer. This is the concentration of CS2. Alright, there we go. There. So that actually wasn't so bad. I guess the only really nasty thing about this, unless I missed something, is this. Because we don't normally deal with 5th roots in math. I'm trying to think if I missed anything. Let's see. Okay, we have some CH4, some H2S, so that's covered by X and Y. 1 liter bulb. At equilibrium, we know the mole amounts of CH4 and H2S, so we know that that's 0.1 molar, 0.3 molar. We know the reaction will proceed forward, so this will change by some amount, this will change by positive amounts. And yeah, I think that's it. For any of you with a textbook, check your answer, or check the answer, I guess. Let's see if I did anything wrong. If I did anything wrong, let me know, and we can see where I went wrong. But as far as I can tell, I do believe this is correct. Yeah, there you go. Alright, so if you guys were following along, then you know, you've probably heard my comments about the other questions and why I didn't bother doing them, because they're very similar to the examples we did. And I picked all the ones that were not the same as the examples we did, so those are actually really fun questions. I like those questions. Anyways, there you go. Hopefully that was helpful to you guys. If you have any questions, come find me tomorrow, I suppose. And yeah, ask me about it. Alright, I am going to sign off.